The topic of this lecture will be oxymercuration-demercuration of alkenes. Oxymercuration-demercuration is a method of hydrating an alkene, adding water across the double bond. However, unlike acid-catalyzed hydration, oxymercuration-demercuration does not go through a carbocation intermediate. Therefore, there is no potential for rearrangements with this reaction. Let's look at the general reaction for the oxymercuration-demercuration of alkenes. In the first step, water is added to the double bond using the mercury catalyst to produce the mercury-containing intermediate. In the next step, sodium borohydride is used to reduce the mercury intermediate. This gives us the final hydrated alkene product. Notice that I have drawn the addition of water, adding anti to the double bond. The hydroxyl group adds to one side of the double bond and the proton to the other. This reaction is stereospecific. We always get the anti-product. And to understand why, we need to look at the mechanism. First, let's look at the mercury catalyst. The structure of mercury diacetate looks like this. I will continue to show the lone pair on mercury because we're not used to seeing the structure of mercury. In the first step of the mechanism, this mercury diacetate loses an acetate group. This produces the active form of the catalyst, along with another acetate group. The mercury cation that is formed then adds to the alkene, the pi bond of the double bond. First, the pi bond attacks the mercury carbocation. The mercury cation. Then the mercury lone pair attacks back to form a cyclic intermediate. It is this electrophilic cyclic intermediate that is attacked by water in order to hydrate the double bond. Water attacks one of the carbons of the cyclic intermediate, kicking off the mercury. It is this step that determines the stereospecific nature of this mechanism, because the water has to attack opposite from the mercury in order to attack the carbon of the cyclic intermediate. And this is why the mercury and the water end up opposite one another on the molecule. Finally, another molecule of water will deprotonate to form the stable mercuric intermediate. Finally, sodium borohydride is used to remove the mercury and replace the mercury carbon bond with a hydrogen carbon bond. You don't need to understand the mechanism for this step. Now let's look at a specific example of this reaction. Let's consider this molecule. If we treat this molecule with mercury diacetate and water, followed by sodium borohydride, we will get a single product, the Markovnikov product. We will not get the less substituted alcohol, or the product that would result from a carbocation rearrangement. Again, this will make more sense once we look at the mechanism. In the first step, the mercury diacetate ionizes to produce acetate ion and the mercury cation. The mercury cation that is formed is then added to the alkene. To form the cyclic mercury intermediate. It is the cyclic intermediate that is attacked by water as the nucleophile. It is at this point that the regiochemistry of addition is determined. The carbon which is attacked by the water as a nucleophile is the carbon that will later contain the hydroxyl group. Water attacks the more substituted carbon of the cyclic intermediate, because this carbon can hold a larger partial positive charge due to its additional substitution. In other words, it has more carbocation character because it is more substituted and can better handle the positive charge. Therefore, the water attacks the more substituted carbon, giving this protonated alcohol intermediate. Next, another molecule of water deprotonates the protonated alcohol. In the final step, sodium borohydride is used to remove the mercury and to produce the final alcohol product. Because we only get the Markovnikov product and not the other possible alcohol products, we say that this reaction is regiospecific. A single regioisomer is formed in this reaction. Additionally, this reaction is stereospecific. Only certain stereoisomers of the product are formed, because the hydroxyl group and the proton that are added across the double bond add in an anti-fashion. Let's look at an example. Let's consider the oxymercuration-demercuration of this molecule. Oxymercuration of this molecule produces only 2 of the 4 possible stereoisomers of the product. In both cases, the water adds anti to the mercury, producing a set of enantiomers. Following reduction and removal of the mercury, we get 2 possible products. Again, this product is a pair of enantiomers, and in both cases the methyls are trans to one another. We can understand why we get only the 2 enantiomers if we look at the mechanism. In the first step of the mechanism, we see the mercury add to the alkene. The double bond attacks the mercury cation, followed by back attack by the lone pair of electrons on the mercury to form the cyclic intermediate. This cyclic intermediate can occur from the top of the ring or the bottom. If attack of mercury occurs from the top, we get this intermediate. If the attack of mercury on the alkene occurs from the bottom, we get this isomer. Attack of water on these intermediates must occur anti to the mercury. Attack of water on the right carbon of the top structure leads to this intermediate. Attack on the right carbon of the bottom structure leads to this intermediate. Deprotonation by water leads to the structures above. You might find it helpful at this point to pause the video and make a model of each of these structures. But it is in this way that this reaction is stereospecific. The hydroxyl group and the proton that are added across the alkene always add anti.